Primordial black holes, the universe's oldest mystery. In the first trillionth of a second after the Big Bang, when the universe was smaller than an atom and hotter than anything we can imagine, something remarkable might have happened. Tiny ripples in the fabric of spacetime, quantum fluctuations in density, could have collapsed in on themselves with such force that they created black holes. Not the kind that form from dying stars billions of years later, but primordial black holes, born in the cosmic furnace of creation itself. These aren't your typical stellar mass black holes. We're talking about objects that could range from the mass of a mountain compressed into a space smaller than a proton, all the way up to millions of times the mass of our Sun. They would have formed before the first atoms existed, before light could even travel freely through space, in an era so extreme that the very laws of physics we know today were just beginning to take shape. Picture the early universe as an incredibly dense soup of energy and matter, fluctuating wildly at the quantum level. In some regions, these fluctuations were so intense that gravity won the battle against the expansion of space itself. These pockets of extreme density collapsed directly into black holes, bypassing the entire stellar evolution process that normally takes billions of years. No star needed to live and die. No supernova required. Just pure gravitational collapse in the cosmic dawn. The fascinating thing about primordial black holes is their diversity. A black hole with the mass of an asteroid would be about the size of a single atom. One with Earth's mass would fit in the palm of your hand, if you could somehow survive the experience. And the largest primordial black holes could dwarf entire galaxies, seeds that might have grown into the supermassive black holes we observe at the centers of galaxies today. This raises an intriguing possibility. What if those mysterious giants at galactic cores didn't form from the accumulation of matter over billions of years, but were actually there from the very beginning, cosmic relics waiting for galaxies to form around them? Now here's where things get really interesting. We've spent decades searching for dark matter, the invisible substance that makes up about 85% of all matter in the universe. We know it's there because we can see its gravitational effects. Galaxies rotate too fast to hold together based on visible matter alone. Galaxy clusters bend light in ways that require much more mass than we can account for. The cosmic web of structure throughout the universe couldn't have formed without dark matter's gravitational scaffolding. But despite our best efforts, we haven't directly detected a single dark matter particle. What if we've been looking for the wrong thing? What if some portion of dark matter isn't exotic particles at all, but primordial black holes scattered throughout the cosmos like invisible seeds planted at the moment of creation? They would be completely dark, detectable only through their gravitational influence, which is exactly what we observe. They wouldn't interact with light or normal matter except through gravity, making them perfect dark matter candidates. The mathematics of this idea are surprisingly elegant. If primordial black holes formed with a certain distribution of masses, concentrated in specific ranges, they could account for a significant fraction of dark matter without contradicting any observations we've made. They could be hiding in plain sight, or rather, hiding in complete darkness, woven through galaxies and galaxy clusters, providing the extra gravity needed to explain what we see. But testing this hypothesis is where the real detective work begins. When a massive object passes in front of a distant star, its gravity bends the light around it, briefly making the star appear brighter. This is called gravitational microlensing, and it's one of our best tools for hunting invisible objects in space. Surveys have monitored millions of stars looking for these telltale brightening events. The results are tantalizing but inconclusive. We've detected microlensing events that could be caused by primordial black holes. But they could also be caused by regular stars or stellar mass black holes. The universe isn't making this easy for us. There's another way these ancient objects might reveal themselves. Stephen Hawking discovered that black holes aren't entirely black. They emit radiation through quantum effects at their event horizons, slowly evaporating over time. For stellar mass black holes, this Hawking radiation is negligible, taking longer than the age of the universe to make any difference. But for small primordial black holes, those with masses less than a large mountain, the radiation becomes significant. The smallest ones created in the Big Bang would have evaporated completely by now in brilliant bursts of gamma rays. Black holes with just the right mass would be evaporating right now, today, releasing their final energy in detectable explosions. We've searched for these death throes of primordial black holes with gamma-ray telescopes, looking for the characteristic signature of a small black hole's final moments. So far, we haven't found anything conclusive. This tells us that if primordial black holes exist, they probably don't exist in certain mass ranges. It's a process of elimination, narrowing down the possibilities, constraining where and how these objects might hide. The formation mechanism itself presents fascinating puzzles. For primordial black holes to form, the early universe needed regions where density fluctuations were much larger than the average. These fluctuations would need to be rare and special, occurring in just the right conditions. Some models suggest they could form during cosmic inflation, that brief period of exponential expansion in the universe's first moments. Others propose they formed during phase transitions, cosmic events where the universe fundamentally changed state, like water freezing into ice but on a scale that encompasses all of reality. One particularly intriguing scenario involves cosmic strings, hypothetical one-dimensional defects in spacetime left over from the early universe. If these cosmic strings existed and collapsed in specific ways, they could have created loops that pinched off into primordial black holes. It's like the universe was knitting itself into existence, and occasionally, knots formed in the cosmic fabric. The implications extend far beyond dark matter. If primordial black holes exist, they're windows into physics at energy scales we can never hope to recreate in particle accelerators. They encode information about the state of the universe when it was unimaginably hot and dense, when quantum mechanics and gravity were dancing together in ways we're still trying to understand. Every primordial black hole would be a fossil from the Big Bang, preserved perfectly by the physics of event horizons. Consider the recent detections of gravitational waves from merging black holes. The LIGO and Virgo observatories have opened a new way of observing the universe, listening to ripples in spacetime itself. Some of the black hole mergers we've detected involve masses that are difficult to explain through stellar evolution alone. Could some of these be primordial black holes, finally revealing themselves after hiding for over 13 billion years? The possibility is genuine. If two primordial black holes happen to find each other in the darkness of space, drawn together by their mutual gravity over cosmic timescales, they would eventually spiral inward and merge, releasing tremendous amounts of energy as gravitational waves. The statistical analysis of these gravitational wave detections is ongoing. Scientists are looking for patterns, signatures that might distinguish primordial black holes from their stellar-born cousins. The distribution of masses, the rate of mergers, the locations where they occur, all of these factors provide clues. It's painstaking work, building up a statistical picture event by event, merger by merger. There's also the question of what happens to matter that falls into a primordial black hole. Unlike stellar black holes that might have accretion disks of swirling matter giving off radiation, small primordial black holes drifting through the diffuse matter of space would accrete material extremely slowly. They'd be nearly impossible to detect through this process. But if one happened to pass through a dense region, like a molecular cloud or even a star, it could create unusual signatures. Some researchers have proposed that certain unexplained astronomical phenomena could be the result of primordial black holes tearing through normal matter. Imagine a primordial black hole passing through Earth. Depending on its size, it might pass straight through without anyone noticing, creating a microscopic tunnel through the planet that would close immediately behind it. Or it might trigger detectable seismic activity. Scientists have actually looked for evidence of such events in seismic records and haven't found anything convincing, which places limits on how many primordial black holes of certain masses can be wandering through our solar system. The connection to galaxy formation is particularly compelling. We observe supermassive black holes in galaxies that formed very early in cosmic history, sometimes less than 1 billion years after the Big Bang. Growing a black hole to millions or billions of solar masses in such a short time through normal accretion is challenging. It requires matter to fall in at nearly the maximum possible rate for extended periods. But if these galaxies started with primordial black hole seeds already in place, massive objects from the very beginning, then the timeline becomes much more reasonable. The seed just needs to grow, not form from scratch. Current cosmological simulations are beginning to incorporate primordial black holes as potential ingredients in galaxy formation. The results are fascinating. In some scenarios, primordial black holes could have helped structure form faster in the early universe, acting as gravitational anchors around which normal matter could accumulate. They might have jump-started the process of galaxy formation, changing the entire history of cosmic structure. But we need to be careful about invoking primordial black holes to solve too many problems. Science has seen many theories of everything that try to explain multiple phenomena with a single mechanism, only to find that nature is more subtle and complex. Primordial black holes might explain some dark matter. They might seed some supermassive black holes. They might contribute to gravitational wave events. But they probably don't explain everything. The universe tends to be diverse in its solutions. The search for primordial black holes represents something profound about how science works. We start with a theoretical possibility, something that emerges from our equations and our understanding of physics. We then ask what consequences this possibility would have, what signatures it would leave in the universe. Finally, we go looking for those signatures with increasingly sophisticated instruments and techniques. Sometimes we find what we're looking for. More often, we find something unexpected that leads us in new directions. The next generation of telescopes and detectors will dramatically improve our ability to hunt for primordial black holes. The James Webb Space Telescope is already probing the early universe with unprecedented clarity, looking at galaxies and structures that formed when the cosmos was young. If supermassive black holes appear too early or too abundantly in these observations, it would strengthen the case for primordial origins. Future gravitational wave observatories, more sensitive than current ones, will detect fainter mergers from greater distances, potentially revealing populations of black holes we've never seen before. There are also proposed experiments specifically designed to hunt for small primordial black holes in our cosmic neighborhood. If tiny black holes are constantly passing through the solar system, they might occasionally come close to Earth. Their gravitational fields, though small, could potentially be detected through their effects on sensitive instruments. It's an incredibly challenging measurement, requiring us to detect gravitational fluctuations far smaller than anything we've measured before, but the technology is advancing. One of the most exciting aspects of primordial black holes is how they connect different areas of physics. They link cosmology, the study of the universe as a whole, with quantum mechanics, which governs the smallest scales of reality. They connect observations of gravitational waves with theories about dark matter. They bridge the gap between the universe's first moments and its current structure. In many ways, primordial black holes are a nexus point where multiple threads of modern physics come together. The philosophical implications are equally intriguing. If primordial black holes exist and make up a significant portion of dark matter, it means we've been sharing the universe with invisible relics from creation itself. They would have been here before the first stars ignited, before galaxies formed, before life emerged anywhere in the cosmos. They would be travelers from an era so different from our current universe that we can barely imagine it. Every primordial black hole would carry within its event horizon information about conditions when spacetime was just beginning to unfold. Consider also what this means for the nature of matter and energy. We often think of the matter we see, atoms and molecules, as the fundamental stuff of reality. But it might be that the universe's inventory includes objects that formed through pure gravitational collapse, bypassing chemistry and atomic physics entirely. Primordial black holes would be regions where matter isn't made of particles in the conventional sense, but is instead just curved spacetime, gravity made manifest. The research continues, growing more sophisticated with each passing year. International collaborations bring together cosmologists, particle physicists, gravitational wave astronomers, and theorists to attack the problem from multiple angles. Data from different experiments and observations are combined, analyzed, and reanalyzed. New theoretical models are proposed and tested against observational constraints. Slowly, methodically, we're narrowing down the possibilities. Whether primordial black holes exist remains an open question. They might be abundant throughout the universe, hiding in plain sight as dark matter. They might be rare curiosities, interesting but not cosmologically significant. Or they might not exist at all, artifacts of theories that don't quite match reality. Each of these outcomes would tell us something profound about the universe and its history. What makes this search so compelling is how it pushes at the boundaries of what we know. It requires us to think about physics in extreme conditions, to consider possibilities that seem almost like science fiction but are grounded in solid theoretical foundations. It challenges us to develop new technologies and techniques to detect things we've never seen before. It reminds us that despite all we've learned about the cosmos, mysteries remain, deep and fundamental mysteries about the nature of reality itself. The universe is under no obligation to reveal its secrets easily. Every major discovery in astronomy has required patience, ingenuity, and often a bit of luck. The cosmic microwave background was discovered accidentally. The first exoplanets were found after decades of failed searches. Gravitational waves were detected a century after Einstein predicted them. If primordial black holes exist, we'll find them, but it might take time, new instruments, new ideas, new ways of looking at the data we already have. And that's the beauty of this kind of science. We're not just cataloging what exists. We're asking fundamental questions about how the universe began, what it's made of, and how it evolved from a hot, dense state into the vast, structured cosmos we observe today. Primordial black holes, if they exist, are witnesses to that transformation. They've seen everything, experience the entire history of the universe from the inside out, though they can never tell us their stories directly. We have to infer, deduce, calculate, and observe, piecing together the narrative from fragmentary clues. The mathematics underlying all of this is both beautiful and complex. General relativity tells us how spacetime curves in response to matter and energy. Quantum mechanics describes the behavior of fields and particles at tiny scales. Combining these theories in the extreme environment of the early universe requires sophisticated calculations that push the limits of what we can compute. Each new theoretical insight might point us toward new observational tests, new ways to confirm or rule out the existence of these primordial objects. In recent years, the quality of cosmological data has improved dramatically. We know the expansion rate of the universe, the proportions of ordinary matter, and dark energy, the spectrum of initial density fluctuations, all with remarkable precision. This allows us to make much more definitive statements about what's possible. If primordial black holes exist with certain masses and abundances, they would affect these cosmological observables in specific ways. We can calculate what those effects would be and compare them to measurements. The constraints are tightening. For some mass ranges, we can already say with confidence that primordial black holes cannot make up all of dark matter. There simply aren't enough of them, or they would have created observable effects we don't see. But other mass ranges remain open, windows of possibility where these objects could still be hiding. The most promising windows are for black holes with masses similar to asteroids, or for those with masses around 30 times the Sun, or for very massive ones that could serve as seeds for supermassive black holes. This is how science progresses in practice. Not usually through sudden revelations, but through the gradual accumulation of evidence, the patient testing of hypotheses, the slow construction of understanding from countless observations and calculations. Each negative result, each constraint that rules out a possibility, is valuable. It narrows the search space, tells us where not to look, refines our theories. There's something deeply satisfying about this process. We're using instruments and techniques developed by humans, from our small planet orbiting an average star, to probe the earliest moments of cosmic history. We're testing ideas about objects so strange that they challenge our intuition, using mathematics developed over centuries of human thought. The fact that we can even ask these questions, let alone begin to answer them, is remarkable. The story of primordial black holes is still being written. New chapters are added with each gravitational wave detection, each deep sky survey, each theoretical breakthrough. Perhaps future observations will confirm their existence beyond doubt, revealing a population of these ancient objects scattered throughout space. Perhaps we'll rule them out entirely, learning that the early universe didn't produce black holes after all, or only in negligible quantities. Either way, we'll know more about reality than we did before. This is the frontier of cosmology, where observation meets theory, where mathematics describes reality in its most extreme forms, where the universe's past illuminates its present. Primordial black holes represent just one thread in the vast tapestry of cosmic mystery, but it's a thread that connects to so much else, that touches on fundamental questions about existence itself. As we look up at the night sky, most of what we see is deceptive. The visible matter, the stars and galaxies, represent only a tiny fraction of what exists. The rest is dark, invisible, known only through its gravitational pull. Some of that darkness might be particles we've never detected. Some might be fields or forces we've never imagined. And some, just perhaps, might be black holes from the dawn of time, relics from when the universe was young and wild and unimaginably different from today. The search continues, driven by curiosity and the conviction that understanding the universe is one of humanity's greatest endeavors. Whether we're right about primordial black holes or not, the journey of discovering the truth is itself valuable, pushing the boundaries of knowledge, developing new technologies, training new generations of scientists, and revealing just how strange and wonderful reality can be. The quest to understand primordial black holes forces us to confront some of the most challenging questions in physics. At the boundary where quantum mechanics meets general relativity, our current theories begin to break down. We know both frameworks are correct in their respective domains, quantum mechanics governing the subatomic realm and general relativity describing gravity and spacetime. But when we try to combine them, when we look at objects like black holes at quantum scales, the mathematics becomes treacherous and our intuitions fail us. Stephen Hawking's realization that black holes emit radiation was revolutionary precisely because it bridged these two worlds. He showed that quantum effects near the event horizon cause black holes to radiate particles, losing mass over time. For primordial black holes, especially tiny ones, this process would be rapid and violent. A black hole with the mass of a large building would evaporate in seconds, releasing energy equivalent to millions of nuclear weapons. The fact that we don't see these explosions happening tells us something important about either the absence of such black holes or the limits of our understanding. But there's a deeper puzzle here, one that keeps theoretical physicists awake at night. When a black hole evaporates completely, what happens to the information about everything that fell into it? Quantum mechanics insists that information cannot be destroyed. The laws of physics must be reversible in principle. You should be able to reconstruct the past from the present, even if it's impossibly difficult in practice. But if a black hole swallows a book and then evaporates into random thermal radiation, where did the information in that book go? This is the black hole information paradox, and it might be telling us that our understanding of either quantum mechanics or gravity or both is incomplete. Primordial black holes make this paradox even more acute. They would have formed from pure energy in the early universe, evolved for billions of years, possibly absorbed matter throughout cosmic history, and some would be evaporating right now. Each one is a natural laboratory for testing quantum gravity, the still theoretical framework that would unify our understanding of the very large and the very small. If we could detect and study an evaporating primordial black hole, we might glimpse physics beyond our current theories. The mass spectrum of primordial black holes, if they exist, would tell us about the nature of fluctuations in the very early universe. Different inflationary models, different theories about how the universe expanded exponentially in its first fraction of a second, predict different patterns of density fluctuations. These fluctuations are what eventually grew into galaxies and galaxy clusters, but in rare, extreme cases, they might have collapsed immediately into black holes. By studying what masses of primordial black holes exist and in what abundances, we could effectively see back to the inflationary epoch, testing theories about what happened when the universe was less than a billionth of a trillionth of a second old. Think about what that means. The cosmic microwave background, our oldest direct view of the universe, shows us how things looked about 300,000 years after the Big Bang. That's when the universe finally cooled enough for light to travel freely. Everything before that is hidden behind an opaque wall of hot plasma. But primordial black holes, if they exist, would be fossils from far, far earlier, from an epoch we can probe in no other way. They would be messengers from a time before time as we know it had properly begun. Recent theoretical work has explored increasingly exotic formation scenarios. Some researchers propose that primordial black holes could form at the end of cosmic inflation, during the transition when the exponential expansion stopped and the universe filled with particles and radiation. Others suggest they might form during the quantum chromodynamic phase transition, when quarks and gluons first bound together into protons and neutrons. Each scenario would produce primordial black holes with characteristic mass ranges and properties, giving us different predictions to test. There's also fascinating work on the possibility of primordial black holes affecting the chemical evolution of the universe. When the very first stars formed, they created heavy elements through nuclear fusion and distributed them through supernovae. But if primordial black holes were abundant, they might have disrupted this process in subtle ways, changing when and where certain elements appeared. By studying the chemical composition of the oldest stars we can find, we might detect the fingerprints of primordial black holes influencing early cosmic chemistry. The gravitational effects of primordial black holes on their surroundings offer another avenue for detection. Even if a primordial black hole is isolated in empty space, its gravity affects the geometry of spacetime around it. Light from distant objects passing near the black hole would be deflected and distorted in specific ways. With sufficiently precise astrometric measurements, tracking the exact positions of millions of stars over time, we might detect the gravitational influence of passing primordial black holes through the tiny shifts they cause in stellar positions. This technique requires extraordinary precision, measuring movements smaller than the width of a human hair seen from thousands of kilometers away, but upcoming space telescopes will approach this sensitivity. The possibility that primordial black holes could cluster together is particularly intriguing. If they make up a significant fraction of dark matter, they wouldn't be uniformly distributed. Like all dark matter, they would clump into halos around galaxies and within galaxy clusters. This clustering would affect their collision and merger rates. Two primordial black holes in a dense environment are much more likely to eventually find each other than two isolated in empty space. The gravitational wave signals from these mergers would carry information about how primordial black holes are distributed, potentially distinguishing them from the stellar black holes we know form from dying stars. Some of the most creative proposals for detecting primordial black holes involve looking for their effects on objects we can observe more easily. For instance, if a primordial black hole passed through a white dwarf star, it would heat the interior through friction, potentially causing detectable changes in the star's brightness or spectrum. If one passed through a neutron star, it might trigger exotic nuclear reactions or even be captured, eventually consuming the neutron star from within over millions of years. These are rare events, but with modern all-sky surveys monitoring billions of stars, rare events become observable if we know what to look for. The relationship between primordial black holes and the cosmic web of large-scale structure is another frontier of research. The universe isn't uniform. Matter is distributed in vast filaments and sheets surrounding enormous voids, a pattern called the cosmic web. This structure grew from tiny density fluctuations in the early universe, amplified by gravity over billions of years. If primordial black holes exist in significant numbers, they would have contributed to this gravitational amplification, potentially leaving subtle imprints in the statistics of how galaxies are distributed across cosmic scales. Advanced computer simulations are now sophisticated enough to model universes with primordial black holes included and compare them to universes without. These simulations start with initial conditions based on measurements of the early universe and evolve forward in time, computing how gravity pulls matter together into stars and galaxies. By including primordial black holes in these simulations with different masses and abundances, researchers can predict what observational signatures we should see. So far, The simulation suggests that primordial black holes could fit into our understanding of cosmic structure, but only if they exist within certain narrow parameters. The connection to particle physics is particularly deep. If primordial black holes formed at certain specific times in the early universe, they would encode information about phase transitions, moments when the fundamental forces of nature changed their behavior. In the first microsecond after the Big Bang, as the universe cooled, the strong nuclear force, weak nuclear force, and electromagnetic force were unified differently than they are today. They separated in stages, each separation a phase transition that might have created conditions favorable for primordial black hole formation. Finding primordial black holes would thus give us experimental data about particle physics at energy scales 1 trillion times higher than we can achieve in the Large Hadron Collider. Consider the implications for theories of quantum gravity. String theory, loop quantum gravity, and other candidate theories make predictions about what happens at the Planck scale, the smallest meaningful distance in physics, about 10 trillion times smaller than an atomic nucleus. These theories are extremely difficult to test because we can't build experiments that probe such tiny distances directly. But the very early universe was a natural Planck-scale laboratory, and any primordial black holes that formed then would carry signatures of whatever quantum gravitational physics was operating. They're like messages in bottles thrown from the shores of quantum gravity's realm. The possibility of intermediate mass primordial black holes, those with masses between stellar black holes and supermassive ones, is especially intriguing because this mass range is otherwise difficult to explain. We know how stellar black holes form from collapsing stars, and we have theories about supermassive black holes growing at galactic centers, but intermediate masses are puzzling. They're too large to form from any individual star we know about, but too small to be the end result of the processes that build supermassive black holes. If primordial black holes could form in this mass range, they would fill a gap in our understanding. Recent gravitational wave observations have actually detected several black hole mergers involving masses in this intermediate range. These detections have sparked intense debate about whether we're seeing primordial black holes or whether there are formation channels for stellar black holes we don't fully understand. Perhaps stars can grow larger than we thought in certain environments. Perhaps black holes can merge multiple times, building up mass in stages. Or perhaps we're finally seeing evidence of primordial black holes. Distinguishing between these possibilities requires more detections, better statistics, and careful analysis of the properties of each merger. The effect of primordial black holes on cosmic reionization presents another testing ground. About a few 100 million years after the Big Bang, the first stars and galaxies began to form, and their radiation ionized the neutral hydrogen gas that filled the universe. This reionization epoch fundamentally changed the properties of intergalactic space. If primordial black holes were abundant, they might have contributed to reionization through the radiation emitted by gas falling onto them, or they might have altered the timeline of when reionization occurred. Observations of the most distant galaxies and measurements of the ionization state of early intergalactic gas can constrain these possibilities. There's a beautiful symmetry to the science here. We use observations of the largest scales, the distribution of galaxies across billions of light-years, to constrain properties of some of the smallest, most compact objects imaginable. We use the faintest signals, barely detectable ripples in spacetime from merging black holes billions of light-years away, to learn about conditions when the universe was almost infinitesimally small. We connect the very beginning of time to the present moment through chains of logical inference and mathematical reasoning. The role of primordial black holes in generating the seeds for supermassive black holes has become increasingly compelling as observations of the early universe improve. The James Webb Space Telescope has now observed galaxies containing supermassive black holes less than 700 million years after the Big Bang. Growing a billion solar mass black hole from a stellar seed in such a short time requires matter to fall in at absolutely the maximum rate allowed by physics. Continuously, for hundreds of millions of years. This isn't impossible, but it's challenging to explain. Starting with a primordial black hole seed of even just 1,000 solar masses makes the problem much more tractable. Moreover, the observed correlations between supermassive black holes and their host galaxies, like the relationship between black hole mass and the velocity dispersion of stars in the galactic bulge, might be easier to explain if black holes formed first and galaxies assembled around them, rather than the other way around. This would flip our understanding of galaxy formation on its head. Instead of galaxies forming and then creating central black holes, perhaps primordial black holes acted as gravitational anchors, cosmic seeds that attracted matter and catalyzed galaxy formation. The implications for the ultimate fate of the universe are also worth considering. If primordial black holes exist in great numbers, they represent a significant fraction of the universe's mass. Over timescales that dwarf the current age of the universe, these black holes would continue to merge with each other, slowly collecting into larger and larger objects. In the unimaginably distant future, trillions upon trillions of years from now, when all stars have burned out and the universe is dark and cold, these black holes might be among the last remnants of structure, slowly evaporating through Hawking radiation in the final eras of cosmic history. But let's return to the present and the practical challenges of the search. One major difficulty is that we're looking for objects that produce almost no light, in a universe filled with luminous matter. It's like searching for black pebbles on a beach at night using only the faint starlight, except the beach is billions of light years across. We need indirect methods, clever techniques that reveal the invisible through its effects on the visible. Gravitational lensing by primordial black holes offers one of the most promising detection methods. When a massive object passes between us and a distant star, its gravity bends the star's light, creating a temporary brightening event. For primordial black holes in certain mass ranges, these events would last hours to months, depending on the black hole's mass and distance. Multiple telescopes now monitor millions of stars simultaneously, looking for these telltale flickers. The challenge is distinguishing black hole lensing events from other phenomena that can cause stars to brighten, like variable stars, supernovae, or lensing by ordinary stellar objects. The statistics are daunting. To detect enough lensing events to prove primordial black holes exist requires monitoring vast numbers of stars for years or decades. Each detected event must be carefully analyzed to rule out alternative explanations. But the payoff would be enormous. A clear detection of gravitational lensing by primordial black holes would not only confirm their existence but also measure their abundance and mass distribution, answering multiple questions simultaneously. Another promising approach involves studying the dynamics of wide binary stars, pairs of stars orbiting each other at large distances. If primordial black holes are constantly passing through our galaxy, they would occasionally make close approaches to these binary systems, subtly perturbing their orbits. By measuring the orbital parameters of many wide binaries with high precision and looking for statistical deviations from what we'd expect in the absence of primordial black holes, we might detect their influence. This method is sensitive to different mass ranges than gravitational lensing, providing complementary information. The role of primordial black holes in producing gravitational wave backgrounds is another active area of research. Individual black hole mergers produce gravitational wave signals that we can detect as discrete events. But there should also be a background hum of gravitational waves from countless mergers too distant or too small to resolve individually. The properties of this background depend on the population of black holes throughout cosmic history. If primordial black holes are common, they would contribute to this background in characteristic ways, potentially distinguishable from the contribution of stellar black holes. Future gravitational wave detectors will be sensitive to this background. The Laser Interferometer Space Antenna, LISA, planned for launch in the next decade, will observe gravitational waves at frequencies inaccessible to ground-based detectors. It will be sensitive to mergers of black holes with masses between thousands and millions of solar masses, exactly the range where primordial black holes might lurk. LISA could either detect primordial black holes directly through their mergers or place such strict limits on their abundance that certain formation scenarios would be ruled out entirely. The interplay between theory and observation in this field exemplifies the scientific method at its best. Theorists propose mechanisms for primordial black hole formation, calculate what observable consequences these mechanisms would have, and make predictions. Observers design experiments and surveys to test these predictions, gathering data with ever-improving instruments. When observations constrain or contradict theoretical predictions, theorists refine their models. When observations reveal unexpected phenomena, theorists develop new explanations. The process spirals inward toward truth, even if the path is not always direct. There's also profound philosophical dimension to this research. The question of what makes up dark matter goes to the heart of what we mean by understanding the universe. We've built an extraordinarily successful model of cosmology that explains the cosmic microwave background, the large-scale structure of the universe, the abundances of light elements, and countless other observations. But this model requires that most of the matter in the universe be something we've never directly detected. This is simultaneously humbling and exciting. Humbling because it reminds us how much we don't know. Exciting because it guarantees there are discoveries still to be made. If primordial black holes turn out to be the answer, or part of the answer, to the dark matter mystery, it would be elegantly economical. We wouldn't need to invoke new particles or new forces. Black holes are predicted by general relativity, a theory we've tested extensively and know to be correct in all regimes we can access. We'd simply be saying that the universe made more black holes, earlier in its history, than we previously thought. Sometimes the simplest explanation, working within known physics, is the right one. But if primordial black holes are not the answer, that would be equally valuable to know. It would mean dark matter truly is something exotic, some particle or field we've never encountered in our experiments. It would point us toward new physics beyond our current standard model, potentially involving supersymmetry, extra dimensions, or entirely novel concepts. Either outcome advances our understanding. The technical challenges of this research are immense, but they're driving innovation across multiple fields. Better detectors, more powerful computers, more sophisticated algorithms for analyzing massive datasets, all these tools developed for hunting primordial black holes have applications far beyond cosmology. The techniques for finding faint signals in noisy data, for modeling complex physical systems, for coordinating observations across multiple telescopes, these are skills and technologies that benefit all of science. Meanwhile, the theoretical work continues to deepen. New papers appear regularly, exploring exotic formation mechanisms, calculating observable signatures with greater precision, proposing novel detection methods. The field is vibrant and active, attracting talented researchers from around the world. Conferences bring together observers and theorists, fostering collaborations that span continents and disciplines. The search for primordial black holes has become a truly global scientific endeavor. As our observational capabilities improve, the window for primordial black holes to hide in continues to narrow. Each new survey, each gravitational wave detection, each high-precision measurement of cosmic structure adds constraints. If primordial black holes exist, we're closing in on them. The next decade will likely be decisive. Either we'll find compelling evidence for their existence, or we'll rule them out across most of the plausible parameter space, forcing us to look elsewhere for answers to our questions about dark matter and early universe physics. The beauty of this uncertainty is that it keeps science honest and exciting. We don't know the answer yet. We're genuinely exploring unknown territory, asking questions whose answers aren't predetermined. This is the frontier, where human knowledge meets the vastness of all we don't yet understand. Every observation could be the one that changes everything, that reveals something fundamental about reality we never suspected.